Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. If you've been watching my video series, then you know we are finally into the realm of derivatives. Specifically, we'll start talking about differentiation rules that you encounter in Calc 1, a typical calculus class. But let me just give you a fair warning here that as we move forward, you still have to remember, even though you're going to learn some tricks here, you still have to remember the true definition of a derivative, because that is something that in college your professor, if they're any good, will continually try to sneak out upon you there, so that you can showcase that you remember what the limit definition of a derivative is. So that'll occur on exams, probably every single exam that you take in calculus. So be very aware of that. The tricks are nice, don't get me wrong, but knowing the actual definition can help you with very theoretically challenging problems. That all being said, and that warning being done, let's dive into this. So we're going to focus on derivatives of polynomial functions and exponential functions for a few videos. In this one specifically, we're going to build the theory behind derivatives of polynomials specifically. We're going to spend some time kind of figuring out why the derivatives of polynomials are what they are. We'll prove some things, and then in the next video, we'll actually use those theorems that we end up proving here. So let's go ahead and start. What is the derivative of f of x equals 2/3? Now, I mentioned it in the sentence above. At this point, we need to start developing a more intuitive approach to differentiation rather than just the limit definition all the time. And this is a great starter example to showcase that idea. If I graph this line out, it is just a horizontal line. In fact, let me just quickly sketch it out. It is the horizontal line at a height of 2/3. Y equals 2/3. And remember, the derivative is just asking, what is the slope of your curve at some given point? Well, the slope of this curve right here, no matter what point I consider, the slope of that curve will always be 0. So the slope here is always 0. So therefore, we can sort of conjecture that the derivative of this function must be 0, because everywhere along that horizontal line, the slope is 0. All tangents have slope 0. So we could just suppose that f prime of x is equal to 0. Now, that's not a proof, but that is a reality. And we're actually going to prove it in the next panel or the next screen, so we might as well reserve the proof until then. But it is very true. The derivative of that function is 0. So let's go ahead and see why. And there is the theorem right there. The derivative of a constant, let c be a constant, then the derivative of that constant must be 0. Notice the notation I'm using. I'm trying to get you used to seeing the Leibniz notation. So in fact, let me write that down. Mainly because I don't want students to get used to only one notation. You need this notation for future and more powerful examples. When we get into something called the chain rule, it's very powerful. And then all throughout higher level calculus, multivariable calculus courses, and differential equations, you have to have that notation down. So we might as well just start it now, right? This means the derivative with respect to x of a constant is 0. So let's go ahead and prove that statement. We'll start with the supposition that c is a constant. Additionally, we're just going to go ahead and suppose that our function, f of x, is just equal to that constant. So we have a constant function. There's a specific reason why I want to do that, mainly because I want to take the derivative. And at this point, whether you know the tricks or not, you cannot assume the tricks. At this point, we must use the limit definition to prove this statement. So the limit definition of a derivative is the following. F prime at x is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. We've been working with that for a while, so now we're just using it within proofs. And let's go ahead and simplify this here. This is the limit as h goes to 0. Let's figure out what f is, our function, when we plug in x plus h. Well, here's our function right here. If you were to plug in x plus h, well, there's no x to plug in on the other side of the equal sign. So the other side of the equal sign is still just c. So whether you're looking at f of x or f of x plus h or f of y plus z, it's always, that function's always just going to be the constant c. Therefore, I can replace that numerator, or the functions in the numerator, with c minus c all over h. And of course, that's the limit as h approaches 0 of 0 over h. Remember, algebra, arithmetic before algebra, algebra before trig, trig before pre-cal, pre-cal before you do any calculus. And here's where that comes into play even further. This is 0 over h. Remember, arithmetic before anything else. What is 0 over anything other than 0? It's 0. 0 over any non-zero number is going to be 0. Now, you might say, this is via direct substitution. Well, actually, it's not even via direct substitution. It's just 0. In fact, maybe I should do it this way. I'll say that's the limit as h goes to 0 of 0, because 0 over any non-zero number is 0. And of course, the limit of a constant is the constant itself. And that's it. We've now proven that the derivative of f, which is a constant, is 0, QED. Now, I do want to finish a statement I just started a moment ago. A lot of students will say, yeah, but that's not 0 over something non-zero. That's 0 over 0. And I would respond, no. If you say that's 0 over 0, then you completely misunderstand what a limit is. A limit, as h approaches 0, means that h is not allowed to be 0. It's any number close to 0, but it's not 0 itself. So therefore, that denominator is non-zero, so 0 over a non-zero number is 0. And then the limit of a constant is just the constant, which in this case is 0. So therefore, that derivative is 0. That's a subtlety that's incredibly important. So just be very, very careful. If you end up doing arithmetic on the inside of your limit, which you should always perform arithmetic first, and you end up getting a 0 in the numerator, then that whole entire fraction is just 0, because that numerator is exactly 0, not approaching, but exactly 0. Now that that is settled, I would prefer to stick this theorem in next, mainly because it allows us to have bigger conversations as we move forward. So this theorem is stating that differentiation is what is called linear. That's not something that is necessary for you to know as far as a word goes at this point, but I'm just letting you know, an operation is called linear if when you run that operation, let me give you an example of an operation that, let me give you an example of something that is an operation first. Way back in the day, we had these operations: addition, subtraction, multiplication, and division. Now, those are the basic operations, but then we grew our kind of operations list to include what we call operators. And operators are kind of functions. Actually, they're not just kind of functions, they really are functions. For example, taking the square root, you're transforming whatever's on the inside of that square root symbol into something else when you apply the square root. Same thing with the absolute value, it does something. The same thing with the squaring function, it does something. And I listed out this last one, which is the first power, because I need it for this conversation. Raising a number to the first power is actually a linear operator. What that means is that if I take any two objects and I plug them into that machine called the first power, As long as those two objects, let's say it's f plus some constant times g, because it's the first power, it turns out that first power allows us to split things across. So this is going to be the first power of f plus c times the first power of g. So that is this machine called the first power. If I plug in f plus a constant times a different function g, out pops f to the first power plus that constant times g to the first power. That's what we'd call a linear operator, something that preserves addition and scalar multiplication. You do not need to know that for this course, but that's when I say something is linear, that's what I truthfully mean. And if you wonder if you're like, that seems so confusing, I don't like it, I would agree with you. Yet, I'm going to tell you right now, most students they desire for their operators to be linear. For example, how many times do you think I have seen a student do this? I could probably say at least 100 times in my career, if not more. Probably near to 500 times I've seen that in my career. That is totally not true. If it were true that a plus b quantity squared is a squared plus b squared, then we would say that squaring is called a linear operator because it breaks across addition. And furthermore, if we have a c in there, if we could write it this way, then again, it would be considered linear. Now, you don't need to know all this still, but I'm just letting you know the linearity operator, or an operator being linear, is what most people desire, but it is the type of operation that is rare to find. However, differentiation is a linear operator, which means if I take the derivative of a function plus or minus a constant times a different function, I could actually split that apart into the derivative of the first function plus or minus that constant times the derivative of the second function. As will always be the case in calculus, there is a little bit of a caveat on the back end, provided these derivatives exist. That's the caveat on the back end. How is this going to be true? Well, for a quick explanation, it's because derivatives are limits, and limits actually satisfy that property. But that's a verbal proof. Instead, we need to do a written proof. So let's go ahead and do the written proof right now. So we start with the statement that we're given a couple functions, just like we have up here, f and g are functions. And we also have a constant. And we're also making the supposition that the derivative of f and the derivative of g exist because, well, that's what the theorem requires us to have, as long as those derivatives exist. All right. Now let's go ahead and state from that, just that statement right there, what does that mean? Really, with a proof, that's what you want to say. You say, well, we're going to go ahead and suppose that these are functions and that their derivatives exist. And somebody says, but what does that mean? And you should say, well, that means the following: that the derivatives are equal to those limit definitions of the derivative, and those numbers actually exist. Those values exist. All right, so that's not too bad. Now let's go ahead and consider what we're actually being asked to work with, which is the derivative of f plus or minus the constant times g. Let's go ahead and do that. Consider the derivative with respect to x of the quantity f of x plus or minus c times g of x, and quantity. Well, by definition of a derivative, that should equal to the limit as h goes to 0 of a big old fraction. The first part of the fraction is this argument right here, this whole entire thing evaluated at x plus h. So let's go ahead and just plug in x plus h to that. So in fact, I'm going to write that in blue so we can see it. So it's f of x plus h plus or minus c times g of x plus h. And then remember, I'm just following kind of this format right here. We just evaluated our function that we were handed, this guy right here, at x plus h. And now what we're going to do is we're going to subtract off that same function, this guy right here, that same function, we're going to subtract it off now. Without the x plus h, just the x. So we're going to subtract off, write that down. I'll do that in green here. I'm going to subtract the quantity f of x plus or minus c times g of x. And remember, this is all still just over h by definition of a derivative. Okay, so this is the derivative of that now green highlighted looking piece right there. And so far, so good. Now what I'm going to do is move things around a little bit. Specifically, I'm going to write this as the limit as h goes to 0. And I'm going to grab that blue, well, let me write my fraction bar first. I'm going to grab that blue f of x plus h and the distributed negative f of x. And then I'm going to grab the blue plus or minus c times g of x plus h. And I'm going to grab the distributed minus times that picture. Now, here's the deal. If I multiply the negative and the positive together, I will get a minus. If I multiply the negative and negative together, I get a plus. And then I still have a c times g of x. Now, a lot of people will look at that and say, why don't you just write it as plus or minus? There's a very specific reason why I'm not writing that as a plus or a minus, because it's not. It's a minus plus. What I mean by that is, whenever, let me grab the right highlighter here, whenever this is plus, that is minus. That's what I mean. That order really does matter. Whenever this is minus, that's plus. Again, order totally matters here. So we have to be very, very careful. By the way, this is all still over h. Well, there's good news here. I can do some arithmetic. My arithmetic is just breaking apart a fraction, and we know we can do that. We can write this as two completely separate fractions. The first one being f of x. Let me use the coloring here. The first one being f of x plus h minus f of x. And that is all over h. The second fraction will be the rest of this stuff. I'm going to circle it up. It's the rest of this stuff right here, all over h. And I'm going to factor a c out of that, if you don't mind, and a plus minus. I think that's pretty okay to do. Now here's where people get confused, because I do my proof all at once rather than in little parts. I want to convince you that this is correct. So let me just showcase. If you had, look at the step we were at previously, we had a blue plus minus and a green minus plus, right? If you were to take where we're at now, where we factored off this piece right here, if you were to distribute it here, you would get a plus or minus c g of x plus h, which is exactly what we have right here. And then if you were to distribute it way over here, well, the negative on that green negative would multiply the plus or minus and it'd become a minus plus c g of x, and that's exactly what we have right here. So I'm not lying to you when I factored off that plus or minus c, that it left us with a minus g of x. You can always distribute back through to double check my work, but it is absolutely true. Now that our arithmetic is done, I'm going to use the limit laws here. We have one, maybe two specific limit laws that we're going to use. The two specific limit laws we're going to use are the following. The first one is the limit law that allows us to break a limit across addition. So I'm going to split this across addition here. This becomes the limit as h goes to 0 of f of x plus h minus f of x all over h, and then plus or minus the limit as h goes to 0 of c times g of x plus h minus g of x all over h. Again, that's a limit law allowing us to split limits. And in fact, you could do two limit laws at once if you want to. You could bring that c out in front of that limit. The limit of a constant times a function is the constant times the limit of the function. So those are just limit laws we know we can use if, remember, the subsequent limits exist. And these subsequent limits actually exist because we started with the assumption that f and g were functions where f prime and g prime exist. And this limit right here is f prime, the limit as h goes to 0 of f of x plus h minus f of x over h. And the other limit is g prime. Therefore, scrolling down ever so gently so my screen doesn't get screwy, we see that we have right here, this is f prime of x plus or minus c times g prime of x. What have we just shown? We've just shown that the derivative of f plus or minus c times g of x is the same thing as the derivative with respect to x of f of x plus or minus c times the derivative with respect to x of g of x. And that is actually what the theorem stated. Let me zoom out. Yep, that's literally what this theorem asks us to prove. So this says that whenever you have a derivative of a combination of functions like that, where it's a sum or a difference of functions, you're allowed to pull that apart into two different derivatives. Note here, I did not put multiplication or division between f and g. In fact, that's so important. So I'm going to write QED because we're done with this proof, but I'm going to write a big old warning here. The derivative of the product of functions is definitely not the product of their derivatives. This is going to be a confounding piece for a lot of people. So just when you're working in mathematics, it's not pretending, it's actually truth. The truth is that you're being given a set of rules. Every step of the way along the road through mathematics, another rule is added to your laundry list of rules. And these rules are built from previous rules. So it's not like we're actually creating trillions of rules here. We only have a couple handfuls of rules, true rules in mathematics. Everything else falls out logically from those 10 rules. But a lot of people like to make their own rules. And I'm telling you, if we haven't proven it, then it is not true. And we have not proven that the derivative of a product is the product of derivatives. We've proven that the derivative of a sum or a difference is the sum or difference of derivatives. So that's very, very critical. Do not treat the product of a couple functions as you would the sum of functions when it comes to derivatives. It's very, 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 very dangerous. So I went through all of that to get this to a point where we could just easily start jumping into problems like this. What's the derivative of this function? Well, let's see, the derivative with respect to x of the function 5x minus 2/7. We've just proven that we can pull that apart like a little taffy pull. You can pull that apart into 5 times the derivative of x minus 2/7. Actually, minus the derivative of 2/7. Sorry about that. I'll put parentheses around that. So remember, if I have a constant multiplying, let me put that in green there. I have a constant right here multiplying x. You can factor that off. And then again, this was a difference of two functions, so I broke it into two different derivatives. We happen to know that the derivative of the constant on the back end, that is going to be 0. So we'll go ahead and write that in. This is 5 times the derivative with respect to x of x minus 0. That's why using that linearity property, the fact that you can pull these apart into their own separate little derivatives, is super powerful, so that you don't have to consider this beast as a large problem. You can take it into its little component terms and take derivatives of those. Now remember what the derivative stands for. The derivative stands for the slope of the tangent line at any given moment. Well, if I graphed out y equals x, which is exactly what we're looking at right here, y equals x. If you graph that out, what is the slope of that curve at any given moment? The slope of that curve at any given moment is 1. It rises 1 when it runs 1. It rises another 1 when it runs another 1, and so on and so forth, all day long. So the slope of this curve always is 1. Therefore, just using sheer logic like that, I can easily answer this question without using calculus. I could say, oh, that's 5 times 1 minus 0, which is just 5. Note, use more logic here. G of x is a line with slope 5. So when I ask you what's the derivative of a line of slope 5, it's just the slope, 5. It's always got a slope of 5. Everywhere for any given x value, the slope of that curve is always 5. The slope of the tangent lines to that curve are always 5. So we sort of used a theorem here, but we used logic instead of actually a theorem, which theorems are logic. But instead of having to dive deep into theory, we just used our knowledge of what a line looks like to say, oh no, that has slope 5 at all times. But let's go ahead and formally prove that the derivative of x, which is just the line y equals x, derivative of that line is just 1. Again, we'd start all our proofs with just a let, in this case I'll let f of x equal just the function x. Then if you want to consider its derivative, f prime of x, you just use the limit definition. Again, as I mentioned at the beginning of this lecture, you will have to use the limit definition in a lot of spots in calculus. And so I want to make sure that your knowledge base is very clean and crystal clear with limit definitions of derivatives. It's not that when I evaluate the derivative of x, I'm always going to use a limit. That's not true. It's just you need it for other things. All right. So let's see. We plug in to our function x plus h. Well, plugging in x plus h means the output is x plus h. Plug it in x, the output is x. Well, arithmetic tells us that this limit is now h over h. And arithmetic, again, tells us that that limit is now the limit as h approaches 0 of 1. And our limit laws tell us the limit of a constant is just the constant. We've now just proven that the derivative of the function x is 1, always. QED. You can see these happen very quickly if you have polynomials. Now, all bets are off if you don't have polynomials. Once you step away from polynomials, proofs get a little more daunting, but still, we can do them. All right, just a couple more examples and then we'll leave this video. Or I should say an example and then a theorem. So what is the derivative of h of x, which is equal to x to the 5th? Now I specifically chose this example because I want to remind you of a prerequisite skill. And if you're my student, then you know that I like to sneak that stuff in as often as possible to kind of keep it in your mind. I dislike having a student go through some topic in mathematics and never seeing it again. I'm sure if I was a student, I'd hate that too. I'd be like, why are you teaching me this if I'm never expected to use it? So I decide that it's important to sneak stuff in that you have used, maybe you haven't seen in a while. I like to sneak those into my lecture. So let's go ahead and do that here. What is the derivative of h of x, which is equal to x to the 5th? Well, we know that h prime of x is just going to be the limit. Now, let me change that function name if you don't mind. I'm going to call it capital H, just because I have a little h already in the limit. So let's say that's capital H of h prime of x is equal to the limit as little h, there it goes to 0, of, let me write it this way, capital H evaluated at little x plus little h minus capital H evaluated at x, all over little h. And of course, plugging that stuff into the function that we were handed, we get something gnarly. X plus h to the fifth minus x to the fifth, all over h. Now there are honestly a lot of different ways to approach this, but the easiest is Pascal's triangle. If you want to expand a binomial with a power, you just have to remember Pascal's triangle. So if you're watching me write this out, which I hope you are because your eyes are still open then, you hopefully can see how I'm building this. It's not that I memorize all these lines. It's that you start with the number 1, and then 1 with a 1, and then 1. All the outer edges are 1s, okay? But then the inner stuff that you start getting, like that 2, is just the sum of these two diagonals. This 3 is the sum of 2 and 1. This 3 is the sum of 2 and 1. This 6 is the sum of 3 and 3. This 4 is the sum of 1 and 3, and so on and so forth down the line. So that's Pascal's triangle. It seems like a recreational mathematics thing, like it's not useful for anything, but in fact, it's an incredibly theoretically powerful structure in mathematics. And it's all based upon binomial expansions. For example, if I had a plus b to the 0th power, well, that would equal just 1. If I had a plus b to the 1st power, that would equal 1a plus 1b. Let me highlight that. 1a plus 1b. If, on the other hand, I had a plus b squared, well, that would be 1a squared plus 2ab plus 1b squared. You see where I'm heading with this, right? And if you have a plus b cubed, well, that's going to be 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. Thing you need to note about the powers. I always start, remember it's a plus b? I always start with a to the highest power, the 3rd power. So a to the 3rd, and then b to the 0th. Hard to see, I know. I should probably maybe zoom out and rewrite that. All right, here we go. So I end up doing this in my head. Okay, this is an A, this has an A, this has an A, and that has an A. And they all have B's as well. B, 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 B. The A's start at this power right here, so cubed, and they decrease. 2nd, 1st, and 0th. The B's, on the other hand, start at the 0th power and increase. Notice at any given moment, the sum of their powers, 3 and 0, 2 and 1, 1 and 2, 0 and 3, they're always going to sum up to the ultimate power in the original binomial. So that's how I know, if you've ever seen me do it in a lecture, when I have something like a plus b cubed, I just know immediately, oh, it's just a cubed plus 3a squared b plus 3ab squared plus 1b cubed. That's how I know it's that so quickly. So, that being said, how does that relate to what we're dealing with? I have an x plus h to the 5th. So a couple more rows down along Pascal's triangle here. It doesn't take me long to just chicken scratch out Pascal's triangle, to be very honest with you. And so I'll just follow the pattern for Pascal's and multiply this out. Let me give myself some room. All right, here we go. I have 1x to the 5th plus 5x to the 4th h plus 10 x to the third h squared plus 10 x squared h to the third. Notice the x values, or the powers on x's, are declining while the powers on h's are increasing. All right, so plus 5x h to the fourth, and then finally plus 1 h to the fifth. And we still have a minus x to the fifth off the back end that we have to account for. This is all over h. All right, great. Let's see if anything cancels. Honestly, only two things will, x to the fifth and x to the fifth. Everything else doesn't. My next step, I can just factor an h out of that numerator. So being painstakingly accurate with my work here, I will go ahead and do that, and you don't have to watch all the gory details. And we get there, and you can see easily that the h's cancel here. Now that the h's have canceled out, you can do direct substitution. Direct substitution will kill off any term that has an h because h is tending to 0. And you get this beautiful, via direct substitution, result 5x to the fourth. Now I want to draw your attention to something. It was, our original function that is, was x to the fifth. Its derivative is 5x to the fourth. And I've mentioned it in previous videos that with polynomials, it looks as though when you take a derivative, you lose a power. You go from the parent to the child, it loses something along the way, specifically a power or a degree. And that's exactly what happened here. Now, a lot of people who deal with or have had calculus in the past know the trick that all they really need to do to take the derivative of this function is to grab the exponent, drop it down in front, and subtract 1 from the old exponent. 5x to the fourth is a derivative. And it sure does beat doing this by hand, right? So that's the punchline. And here's the theorem that we're going to prove so that we can use that punchline. You can't use that punchline until we prove this theorem. Something important about this theorem is that it can only be proved right now for natural numbers. We're going to assume it's going to work for all rational numbers, but I'm just letting you know the proof that we can do today will be based upon the natural number system, and that's because we need something called logarithmic differentiation to be able to prove this for all numbers. So for now, the proof will hold for natural numbers, but we're going to go ahead and use it for rational numbers. All right, so here's our proof. We'll start with just allowing our function to equal x to the n, where n is a member of the natural number system. And then we're going to use a trick again, or not a trick, but a proof style that you were introduced to in pre-calculus. And this proof style is called mathematical induction, or the domino proof. The domino proof, or mathematical induction, is very beautiful. It is assumed prerequisite to enter, to set toe into calculus. If you have not learned it, this proof will not make sense to you. And by the way, you will be proving things like this in calculus. So you do need to review the proofs by mathematical induction. I will eventually have a video on that because I'm making a bunch of videos right now for my pre-calculus students. But just to let you know, that is a critical prerequisite. You will have that occur in your homework. You just have to know how to use it. So for those who know, and for those who don't know how to use mathematical induction, here we go. We'll start by proving that this statement is true for n equals 1. So I'll say for n equals 1, the derivative with respect to x of x to the n is actually just the derivative with respect to x of x to the first. But we've just proven on a previous page somewhere that this is going to be 1. And by the way, that is actually n. Remember, we're assuming n is equal to 1 here. That is actually 1 times x to the 1 minus 1, or 1 times x to the 0th. So the claim is at least true for the first domino. We have a bunch of dominoes lined up from 1 to infinity, and we've proven that this claim works for the first domino in line. Now there is a second domino in line, and a third and a fourth and a so on and so forth, all the way down to the kth domino and the k plus first domino and so on and so forth down the line. Okay. So the next part of this proof, all we've done is proved it for one, doesn't mean it's proven for everything, is we're going to assume that it works for n equals k. This is called the induction hypothesis. So we're going to go ahead and assume that the claim is true for n equals k. And then usually for me, I really like to say what that means. So I say that is, just looking back at the theorem, the derivative with respect to x of x to the kth power, we're going to assume that's going to be k times x to the k minus 1. We're going to make that assumption. And what that looks like on the dominoes is that, well, again, in green here, I'll put this in green. This first domino is green lighted. It is tipping over. We've proven it. So it's tipping over. It hasn't touched that second domino yet. In other words, we haven't proven it for the second, that the claim is true for the second domino. We've only proved it for the first. So the first domino's falling. And now we run down the line. It could be a billion steps later, but we're going to assume that this one that I'm coloring right here, which I'll call the kth domino, n equals k, we're going to assume that's falling. In other words, that the claim is true for n equals k. And what we want to do is, with that assumption, we want to prove that the claim must be true for n equals k plus 1. N equals k plus 1 falls as well. That's why we call it the domino proof. So you're assuming that somewhere down the line, some random domino is falling. And with that assumption, if you can prove that the next one in line has to fall, then your random domino that you said was falling could have been the second or the first domino. So if the first domino is falling, that you've just proven that the next one or the second one is falling. But if the second one is falling, you've proven that the third one has to follow because that's the next one in line, and so on and so forth. So let's go back. So we have assumed the claim is true for n equals k. That is, the derivative of x to the k is k times x to the k minus 1. Great. Consider n equals k plus 1. That is, we're going to consider the derivative with respect to x of x to the k plus first power. All right. Now, what you want to do in this argument is use your induction hypothesis, your assumption here. But we'll see if we can do that. Now, by the definition of the derivative of x to the k plus first is just a limit as h goes to 0 of x plus h to the k plus first power minus x to the k plus first power, all being divided by h. Now, this next step, there are a couple ways to go about it. I'm actually going to just use basic algebra for this next step. So I'm going to say that's the limit as h goes to 0, and I really, really, really would like to get these powers to not be k plus 1, because I have made an assumption about the derivative of x to the k. So if I can get that to be x plus h to the k and an x to the k, then I'm good as gold. So what I'm going to do here is I'm going to factor off that first term and x plus h to the first. If I do that, I'm left with an x plus h to the k. You can double check my work there. If this is a first power and that's a kth power, you multiply the same bases, they would add to be k plus 1. So there's nothing mystical or incorrect that I did here. Minus, and I'll do the same thing in the second term. I'll factor off a power of x, that's all. I'm left with an x to the k. This is all over h. So again, nothing super crazy yet. Now what I'm going to do is rearrange. Again, just arithmetic. So, a little bit of algebra. I'm going to distribute. So if I distribute out the x plus h in the first term, I'll get the following. X times x plus h to the k plus h times, again, x plus h to the k, and then minus x times x to the k, all over h. Hopefully you follow that. Now what I'm going to do is I'm going to take this term and I'm going to glue them together in their own fraction. And I'm going to take the remaining term, this guy right here. Oops, that's not what I want. I wanted a highlighter of that color. I'm going to take the remaining term, this guy right here, and I'm going to put it in its own fraction. Let's see what that looks like. That's the limit as h goes to 0 of x times x plus h raised to the k minus x times x to the k all over h. And then plus the limit as h goes to 0 of h times x plus h to the k all over h. So all I did was separate the yellow highlighted stuff into the first limit and the blue highlighted stuff into the second limit. Everything should be okay with you. None of this should be super crazy. Notice that in that first picture, that first limit, both terms in the numerator have this x in common. That x does not rely upon h, so you can actually pull that outside of the limit. Because it does not rely upon h, it's not adjusted as h runs to 0, you can pull that x out. You'd still be left with x plus h to the k minus x to the k all over h, but I'm able to factor out that x. Let me highlight it in yellow. That's what got pulled out. In the second limit, the h's cancel. So I have this plus limit as h goes to 0 of x plus h to the k. Now remember what we did earlier. My whole goal here was to use what we call the induction hypothesis. We made an assumption that the derivative of x to the k was k times x to the k minus 1. Now remember, the derivative of x to the k is actually the same thing as the limit as h goes to 0 of x plus h to the k minus x to the k over h. I'm going to highlight that. And actually, I'm going to highlight that in a totally different color. I'll highlight this here because I want you to see that that limit is exactly what we just arrived at right here. Those are the same pictures. So I can replace that picture with this because that's what that limit is equal to. We assumed that that derivative, which is that limit, is equal to k times x to the k minus 1. So this is going to be x times k times x to the k minus 1 plus, in the second limit over here, we just use direct substitution. Let h be 0 and you get x to the k. And notice what this looks like. X to the first times x to the k minus 1. That'll be x to the k. And if you factor out the x to the k, you'll have k plus 1 times x to the k. And I kind of forgot to mention it in the beginning. However, usually when I do a proof by mathematical induction, when I get to this step where I say, well, let's go ahead and let n equal k plus 1. Off to the side, I usually write what we want to show. So let me go ahead and write down what we wanted to show, right? I want to show that the derivative of x to the k plus 1 is actually, so I want to show, let me write that down. I want to show that the derivative with respect to x of x to the k plus 1 is equal to k plus 1 times x to the k. That's what I want to show, because then that would showcase this theorem that if I let this n be k plus 1, its derivative would be k plus 1 times x to the k. Okay. So notice, sorry, my screen does that. Don't 100% know why it does that, honestly. But notice in the end, I actually get what I wanted to arrive at. I wanted to arrive at k plus 1 times x to the k, and I have it. Which means that as long as our assumption is true, as long as the kth domino is falling, we have proven, therefore, that the k plus first domino must also fall. Since k was arbitrary, it could be 1, which means the second one is now falling. But because k was arbitrary, it could be 2, which means the third is now falling. And now we've proven that all dominoes are falling. That's how a proof by mathematical induction is done. It's, again, a really nice proof style. It works great if you have a claim based on the natural numbers. So I'm going to write implies or thus. The claim is true by mathematical induction, and it's only true for natural numbered n values. Now, that's not exactly true. The claim is actually true for all rational numbers, but right now, that proof, we've only proved it works for natural numbers. We're going to assume it works for rational numbers, but I'm just letting you know that proof is a little bit, requires a little bit more mathematical technology than we currently have. But here's the proof on one page in all of its glory. So now you know the derivative of x to the n, just bring down the power, reduce 1 from the power, you're done.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.